Okay, so I'm going to give you a brief introduction or a brief overview on one of the recent Life publications. It's sort of the follow-up publication to Life paper 3, which I presented in a previous meeting where we looked at an Earth-like exoplanet. Here in Life paper 9, we sort of started looking into clouds by studying a Venus-like exoplanet. And the main questions we try to answer is, can we easily differentiate between a Venus-like planet and an Earth-like planet? And then the second question we try to answer is, can we find evidence for clouds in Venus's atmosphere by using life to study Venus's mid-infrared thermal emission spectrum? So very briefly, just the most important take-home messages from Life paper 3, because this new paper builds on findings from the third paper. In the third paper, we really try to find constraints on the requirements for life by studying an Earth-like atmosphere. So we ran retrievals on various different spectra and changed resolution, signal-to-noise ratio, and wavelength coverage. And this sort of gave us first estimates for what we need to arrive at a decent characterization with life. So we found that we need a wavelength coverage of at least 4 to 18.5 micron, a spectral resolution greater than 50, and a signal-to-noise ratio of at least 10. However, in this first study, we neglected a lot of important factors. I would like to highlight two. One of them was that we basically ran all retrievals using exactly the same model that we used to generate the spectrum. Now, of course, for an exoplanet, we will not know what the atmosphere looks like, and thus we will not know which model to use necessarily. And the second thing that we did is we neglected clouds in this first study. So those are the two major limitations of this study. So in Life paper 9, we took a closer look at Venus. And the interesting thing about Venus is that we really have a thick, opaque sulfuric acid cloud layer in sort of between 0.1 bar and 1 bar in Venus's atmosphere. However, Venus's atmosphere extends all the way to 93 bars. So we have a cloud layer relatively high up in the atmosphere, which has a significant impact on the spectrum. So what we did in the study is we first modeled the emission of a Venus-like atmosphere by using Petit-Ratrans, which is a one-dimensional basically, we used a one-dimensional atmosphere model and then calculated the spectrum using Petit-Ratrans. In this atmosphere, we considered different molecular opacities. We accounted for water, carbon dioxide, and CO, which are basically the main molecules present above Venus's sulfuric acid cloud layer. And then, of course, we modeled we had a very simple model for the sulfuric acid clouds. And then we simulated observations of this Venus-like planet with life. We put this planet on a 0.72 astronomical unit orbit around a sun-like star, so it's really a Venus twin situation. We placed the system 10 parsecs away from the observer, and then considered different spectral resolutions. And then we used LiveSim to predict the noise levels that we would expect with life. And we sort of considered different noise levels on this Venus-like spectrum. This then gave us a spectrum that looked something like this. This is a resolution 100 spectrum and the signal-to-noise level of 10 with life. And then we ran retrievals on this spectrum to try and constrain parameters such as the surface temperature, the radius of this Venus-like planet, the pressure temperature profile, and we tried to find atmospheric trace gases in Venus's atmosphere, and we also tried to constrain the clouds. And we ran these retrievals with two different forward models. One forward model that we used was sort of the true sulfuric acid cloud model. So we assumed that there are clouds present in that atmosphere. And the second model we ran retrievals with on all spectra was a cloud-free atmosphere model. So we basically made a wrong assumption that there were no clouds in Venus's atmosphere and tested what our retrieval would predict using the wrong model. Okay, let's look at some of the retrieval results. First, looking at planet parameters, we see that we cannot constrain the surface pressure and the surface temperature, which is not really a surprise because we have this opaque cloud layer high up in the atmosphere, which obscures the view of the surface. In the case of the cloudy model, the model sort of retrieves a Venus-like cloud layer. In the case of the cloud-free model, the retrieval just places the surface of the planet at the cloud top or in Venus's atmosphere. However, we do manage to get quite strong constraints on the equilibrium temperature and the bond albedo of this Venus-like planet, and that's just because we're considering the mid-infrared thermal emission. Yes. Then which trace gases can we detect in the atmosphere? We find CO2, and we can also show that CO2 is the main constituent of Venus's atmosphere, which then also shows us that this planet is clearly different from Earth because it has a CO2-dominated atmosphere, as opposed to Earth, where CO2 is only a trace gas. However, we cannot find carbon monoxide and water, and this is just because in Venus's spectrum, both molecules do not really have strong features, and thus are hard to detect. And these results are independent of the resolution and the signal-to-noise ratio of the spectra that we consider, and they are also independent of whether we use the cloudy or the cloud-free model. Now, the question, of course, is, are there parameters that do depend on resolution and signal-to-noise ratio and also on the model that we use? And what we find in this study is that the retrieved planet radius really depends on the forward model that we use. And this is what I show here in this plot on the right. What I want you to focus on is the thick yellow line, which is the estimate for the planet's radius for the cloud-free model. The other thing is the green histogram, and that is the estimate for the planet radius for the sulfuric acid clouds. So this sulfuric acid cloud model. And what you see is that in the top, so for low spectral resolutions and low signal-to-noise ratios, the cloud-free model yields the best estimates for the planet radius, whereas when we move to high resolutions and high signal-to-noise spectra, we see that the cloud-free model yields a biased estimate for the planet radius. The sulfuric acid cloud model all of a sudden yields a good estimate. So this shows that an inadequate choice of cloud model in this case can really bias our retrieval results. And I'm purposely not saying wrong model, but inadequate model, because what model you choose will depend on the resolution and the signal-to-noise ratio of your spectrum. Now, the last question I would like to talk briefly about is, can we infer clouds with life? And what I'm showing here is a base factor comparison for the cloud-free versus the cloudy model. And what this basically tells you is, if it's red, it means that the cloud-free model performs better. And if it turns green, it means that the cloudy model is preferred so that we can constrain the clouds in Venus's atmosphere. What we see is that for the low resolution and signal-to-noise ratio cases, we basically do better if we use the cloud-free model. And interestingly, this also corresponds to the cases where the cloud-free model yields the better estimates for Venus's radius. Whereas if we go and look at high-quality spectra, this is where we can start to constrain the cloud properties of Venus. So we can start to tell that probably it's sulfuric acid clouds, and we can also start to determine the correct position of the clouds in the atmosphere. And these are then also the cases where the cloudy model yields the better estimates for Venus's radius. So these are just the take-home messages. So in Life 9, we run retrievals on a simulated mid-infrared Venus spectrum to study how life would characterize Venus. And we find that Venus can be easily distinguished by Earth, mainly by determining how much CO2 is in the atmosphere. We also see that clouds can prevent, and this is not really a surprise, the accurate characterization of the surface conditions of a terrestrial exoplanet, and an inadequate model choice or also cloud model choice in retrievals can significantly bias the characterization of an atmosphere. Okay, this is all I wanted to tell you, and I'm happy to take questions.